Hi everyone. Today we're going to discuss half-life, which is a specific example of our exponential growth and decay word problems. So by the end of this, you should be able to set up and solve half-life problems. Now I know it says, but first, what is half-life? But I think it's best explained through an example. Okay, so this is a medical/scientific example, so I'm going to do the best I can to unpack this, but really we're going to focus on the math. So in terms of science, I'll explain what I can, but go ahead and ask your science teacher if you have follow-up questions. So this element, technetium-99m, is a radioisotope used to image the skeleton and heart muscle. Has a half-life of about 6 hours. So these problems often intimidate 2 algebra honors students because of all the big words and then this half-life concept that we've never heard of. So I'm going to try and break it down, and I'm not a science teacher, but I did a little research to figure some of this out. Okay, so technetium is used in the medical world. It is a radioactive isotope. Isotopes have to do with atoms and elements. So from my understanding, what an isotope is it's like the same chemical element with different masses. Radioactive means that it's unstable. Okay, so radioisotope means radioactive isotope. And its use, well, it's talked about here. So it's used to image the skeleton and the heart muscles. So it's used to get a picture of what's inside of you. When I was reading these problems, I was very curious what the M stood for, so I Googled it. And yada, 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 there's all this other stuff talking about technetium. But the M stands for metastable, which means it has an excited nucleus. So again, I don't know a lot about this. Please ask your science teachers more and let me know. But I am going to show you, what half-life means and how to solve problems. So if you're in the medical field or you're studying elements or science or whatever it is you're doing, that you have the math skills to back it up. Okay, now that we've got all that science out of the way, what does half-life mean? Okay, half-life essentially is talking about the time it takes for half of the amount of whatever you're talking about to no longer be radioactive. Now, I'll write this up here in a second, but again, easier to understand through an example. So if it says the half-life of technetium is 6 hours, what that means is after 6 hours, half of the original amount will no longer be radioactive. Okay, so now I'm going to give you the formal definition of half-life. So half-life is the time it takes for the radioactivity for some substance or even more specifically some isotope to fall to half its original value. Half there, that's key. Okay, so after 6 hours, then the technetium is half as radioactive, essentially. Okay, so this is important to understand because this tells you a lot about the math as well and how to set this up and how to calculate this. Because if it's, after 6 hours, it's half its original value, that means we start off larger and are getting smaller. So this is an example of exponential decay. Okay, so half-life in general is an application of exponential decay. You can even write exponential decay. Okay, so if it's exponential decay, I know that the formula has to be P e to the negative RT. Okay, or again, you can always say P sub 0 e to the negative KT. They mean the same thing. Okay, and that'll give me an output of my final amount. So we can call the function whatever we want. It says write a formula for the amount of a 250 milligram dose that remains after T hours. So you can call it, I don't know, if we're talking about dose or we're talking about technetium, like call the function whatever you want. So I'll do D for dose because I don't want to do T of T again. That wasn't fun. Okay, so your goal is to write a formula that remains after T hours. So with that said, at the end of this, you should have D of T only in terms of T, which means that I need to fill in my R and I need to fill in my P. Okay, my P is my initial amount. So what I'm starting with is 250 milligrams. Now, I do not know my rate, so I don't know how fast it's changing over these 6 hours. I just know that the time is 6 hours. So before I can write my equation, I'm going to have to do something to solve for my r. If I want to solve for my r, I need to plug something in for every other variable. So I need to plug in something for t, p, and d of t. So let's figure out what we can plug in to solve for my rate, and then we can write our equation. So I'm starting with 250 milligrams, so that's my p. I said I don't know my r, but I do know that the half-life happens in 6 hours. So I can plug in 6 for my t, because that's how long it takes for it to be half of its original value. Now, if I'm talking about the half-life, then I know that my final amount should be half of my original amount. So my final amount should be 125. Okay, and you've set up this equation solely to solve for r, so you can write a formula. So in order to do this, we're solving an exponential equation. First, you want to take care of anything that's bothering the e, so I'm going to divide by 250. If you divide both sides by 250, you're just going to get 1/2 equals e to the negative, and I'll write this as 6r instead of r6. Okay, so any half-life problem you have, your initial amount should be double the size of the final amount. Okay, so you should always have 1/2 equals this, which makes sense if you think about it, because my final amount is half after 6 hours. So that's what this equation is representing. Okay, now to solve this, you have to get rid of the e. So the inverse of e to the x is the natural log. So I'll take the natural log of both sides. So I have natural log of 1/2 equals negative 6r, because these cancel. Or you can rewrite an exponential, or log form if you aren't sure. Okay, now divide by negative 6, and you'll be able to solve for the rate. So I'm going to plug that in my calculator. Okay, I've done that off to the side, and you should as well. Once you do that, you get the rate is 0.116 or 0.12, however you want to round it. I guess I should say that's approximately. So if we write that as a percentage, that'd be like 11.6%. Okay, but we don't write it as a percentage when we write these formulas. I just wanted to highlight that that is the rate at which our half-life will be moving. Okay, so again, the goal was to write a formula for the amount of a 250 milligram dose that remains after t hours. Okay, so the sole purpose of all this was just to solve for the rate. So when you're doing a half-life problem, you should know your step 1 is to solve for the rate, if it's not given, which usually won't be. Okay, you have to figure out how that's happening. Okay, step 2 will be to write your equation. Write equation. And so I call this d of t. I'll just rewrite that. Okay, my initial is still 250 because that's what I'm starting with. That's my dose. Okay, my e still stays the same. My rate, well, it's going to be negative, but my rate is 0.116. And this function needs to be in terms of time. Okay, so this is how we would calculate how much remains after t hours. So we're no longer necessarily talking about calculating half-life every single time, because you already know the half-life takes 6 hours and the rate is 0.116 or 11.6%. But this will calculate every other case. So how much remains after 52 hours, right? Because we know 6 hours, we have to be able to calculate the rest. That's what this equation does. Okay, so here's an example. Determine the amount of a 250 milligram dose that remains after 24 hours. So we're not really talking about its half-life anymore, but its half-life helped me write this equation that I'm going to use to solve. So d of t is 250 e to the negative 0.116 t. There should be a 250 there, but we know my t is after 24 hours. So it takes 6 hours for half-life, but what happens after 24 hours? So this I'll just plug into my calculator, which I'm going to do off to the side, and get a decimal answer. So if I do that, I got 15.448-ish. Okay, so I'll just round that to 15.45. So that's the amount of milligrams left after 24 hours, which makes sense because after 6 hours, it's going to be half its original value. So after 6 hours, it's like 125. After 24 hours, it's a lot more hours. It's got to be a lot less than that. So there are 15.45 milligrams left. Okay, so moral of the story, its half-life is the time it takes for the radioactivity to be half its original value, blah, blah, blah. But we use that half-life to solve for our rate, so we can set up an equation to figure out what is the decay, or how is the decay affecting the function after any given time. Okay, so please come to class with questions and write them down on your note sheet. Have a great night.